So you might have noticed in this last one that if we were to use direct substitution, we're also going to get 0 in the denominator. Is that a point where we're going to say does not exist as well? Well, in this case, let's look at what happens if we use our direct substitution method. Direct substitution of x equals 3 gives us 3 squared minus 9 divided by 3 minus 3, and yep, we get that 0 in that denominator. But before we go too far, in this case, we get 3 squared, which is 9 minus 9, which is 0 in the numerator. This is termed an indeterminate value. And I'll leave it to you later on here as we discuss this in class why we call it indeterminate in the first place. But it's an indeterminate value. At this point, we're going to stop. We're not going to say it does not exist because there might actually be a value associated with this. And one way of handling it is to say that we have a particular rule. We say that if we have two functions, f of x and g of x, and we say the two functions f of x equals g of x for all x, that's not a very good way of spelling it. If f of x equals g of x for all x, in the domains of f of g, except possibly at x equals c, but we take the limit as x approaches c of f of x and find there's a value, and we take the limit as x approaches c of g of x and find there's a value, what we should find is if these two functions are equal everywhere except at that point c, their limits will equal. And the reason for that is that it doesn't matter whether or not g of x or f of x is defined or undefined at x equals c. We're interested in the behavior near x equals c. So let's see if we can come up with an equivalent function. And we know that x squared minus 9 does factor as x plus 3 times x minus 3. And we're dividing that by x minus 3. And if you recall, one of the things that we developed was the idea that if we have a function that has a common factor in the numerator and denominator, we can rewrite it as an equivalent function as long as we account for that change in the domain. So x could not equal 3 in either case. So in fact, we know that these two functions are equal everywhere. X squared minus 9 over x minus 3 is equal to x plus 3, except at x equals 3, which means we go to our theorem right here, which says that if we really wanted to evaluate the limit as x approaches 3 of x squared minus 9 over x minus 3, it would be exactly the same as if we wanted to evaluate the limit as x approaches 3 of the quantity x plus 3. In this case, that means it goes to the value 6, right? 3 plus 3, that's 6. And so that is actually our limiting value. And we found that on the basis of our rational function by canceling. All right, so this is another tactic. If we get 0 over 0, we're going to try and evaluate a rational function by canceling. So here's a couple more examples. Let's say I'm taking the limit as x approaches negative 2 of x squared plus 5x plus 6 over x plus 2. Well, direct substitution will show, right, we should always do the direct substitution here to indicate this, that we're going to get negative 2 squared plus 5 times negative 2 plus 6 all divided by negative 2 plus 2. And doing the work right here, we get 4 minus 10 plus 6, that's 0, divided by 0. Sure enough, we should do this by factoring and canceling if that's at all possible. So let's figure it out right here. we would factor the numerator. X squared plus 5x plus 6 factors as x plus 2 times x plus 3, revealing a common factor in the numerator and denominator of x plus 2. And we know that these two functions would be alike everywhere except at x equals negative 2, because when we cancel that common factor out, we get the function x plus 3 at every point except x equals negative 2, but it doesn't really matter because in this case, when we put in negative 2, we're going to get y equals 1, and that's our limiting value. All right, how about this last one right here? This looks like a bear. We've got x cubed plus 1 over x plus 1. Well, remember, we can't just cancel out an x cubed and a 1 right here, right? We have to factor and look for any canceling. Well, this is a job for our difference of sum and difference of two cubes. In this case, we know that if we had a cubed plus b cubed, then we could factor that as a plus b times a squared minus ab plus b squared. So making the correct substitutions right here, we could say, well, our quantity x cubed plus 1 divided by x plus 1 is exactly the same as the quantity x plus 1 times x squared minus 1 times x plus 1 divided by x plus 1. Well, that means that the function x squared minus x plus 1 is the same as x cubed plus 1 over x plus 1, except at x equals negative 1. So once again, we have the ability to say that our limit, our original limit, is the same as the limit as x approaches negative 1 of x squared minus x plus 1. And by direct substitution, our evaluation becomes negative 1 squared minus negative 1 plus 1, which is to say 1 minus negative 1 plus 1 plus 1. Sure enough, our limit is equal to 3. More to come.